Okay, hello everyone. Welcome to the 51st and our last online Spintronics seminar of this year. Thank you for joining us. It's my great pleasure to introduce our speaker today. Professor Ahmet Avsar is an experimental physicist working as a lecturer in physics at Newcastle University. Prior to that, he was an EPFL fellow at the Swiss Federal Institute of Technology, Lausanne. He completed his PhD studies in the physics department and Graphene Center of National University of Singapore. He's interested in the exploitation of multiple quantum degrees of freedom, such as spin, charge, Valley, in two-dimensional materials-based heterostructure devices using transport and optical techniques for applications in energy-efficient information technologies. So today he will be talking about spintronics in 2D materials. So with that, Professor Avsar, please take it from here.
Thank you so much for the introduction. So, hi everybody. Before starting my talk, indeed, I would like to thank the Shimpan and the Kirill for organizing these wonderful seminars, and also giving me the opportunity to tell you a bit about my research. So, I recently joined the Newcastle University, and today I will be talking about the spintronics in 2D materials. Okay, so since as all of you are well aware, spintronics is an exciting research area in electronics. Indeed, spintronics has been considered as a complementing or even replacing the charge degree of the freedom in the logic devices. And it's not also like a just conceptually existing topic. Indeed, like I guess it was around 1988-89, Albert and Peter Grunberg, they discovered that in the multi-layer films made of the magnetic and non-magnetic materials, okay, so the resistance of these materials were changing depending on the relative polarization direction of the magnets. So this is like GMR effect, and it got the Nobel Prize for them. But equally important, like all the research that I will be showing you about the spin walls, etc., the geometry, the device architecture, everything was started with this discovery. And indeed, the field is moving, is getting more and more exciting, and there have been like so many proposals which are just aiming at utilizing the spin degree of freedom, for instance, in the logic devices. And despite like there have been like so many proposals which are like aiming to have like high speed, high density memories or the logic operations, the experimental progress is a bit slow. It's mostly related with the materials. And for instance, like there are some like common elements in these components in these material systems. For instance, like you need a spin conducting channel material which can transport spins over long distances, or you need to be able to also manipulate the spins while it's transporting. And sometimes even you need to use this spin current to manipulate the magnetization direction of the output magnet. So we need the material systems. And with the discovery of these 2D materials, with the graphene in particular, so the question was like if these 2D materials are also important for spintronics. Indeed, the answer is yes, and there have been like huge emphasis. And even like European Union's this famous $1 billion euro graphene flagship, it has a special work package just for the spintronics, which is just aiming to investigate the fundamental research as well as really like technological applications based on the 2D materials. And indeed, there have been like hundreds of the materials now which can be isolated to monolayer. And they could be like quite important for spintronics. One of them is like, for instance, the boron nitride. This boron nitride, it has like a crystal structure very similar to the graphene, but instead of the carbon atoms, it has like boron and nitrogen in a hexagonal structure. And this materials, once it's like a few nanometer thick, it's like extremely flat, and people have been using as a substrate to increase the mobility of the materials, hosting materials. But once you go to the 1, 2, 3, a few layers of this material could be used as a very high quality tunnel barrier because it's like almost defect free, and it's also like yeah, almost defect free, and also yeah, very uniform and flat. And the graphene, you are already aware, there have been also like lots of talks about that. So graphene is indeed, I could say that it's the star material in terms of the spintronics. It shows the longest spin relaxation length ever measured in any material system at room temperature. I will be talking a bit about graphene spintronics today, and I will be also talking about the black phosphorus. Black phosphorus is like quite a different material. It has like very different crystal structure. You can see here already, like it has a package structure with armchair and also zigzag edges. And this material, it has quite high mobility. I will show you later, and it's very promising for spintronics. And last 2 years or 3 years, there have been also like a very nice, exciting research on the long-range magnetic ordering in or layer-dependent magnetism in a lot of material systems. Now we come to the point that while we are still investigating this single material's spintronics properties, if you can combine all of them by building some exciting van der Waals heterostructures, you can now do very innovative, like a high quality spin devices. And I have been also working about the magnetism recently. And we realized a long-range magnetic ordering in platinum diselenide. It was a surprising observation. And but since I have already given like 2 talks recently and they are available online, so I decided not to include them today's presentation, but you can look at the videos. And another exciting research direction of the 2D spintronics is the spin orbitronics. There have been like very nice studies recently. The field is really very active, and on this seminar series, Iris Ferreira and also Saradash, they also gave like very nice talks about this subject. So I'm not also going to talk about that, but we recently wrote a review article, so you can go and look if you are interested in this aspect as well. I guess those videos are also available online. So today I will be talking a bit about the graphene spintronics. I will give you an introduction about the graphene spintronics and some of the recent advances. And then later on, I will move with the black phosphorus, the semiconducting spintronics. Here I will show you that the material is like normally air degrading. And if you do good take care of the material, it can be like quite air stable. And you can realize very nice spin transport properties in this material. And finally, of course, I will give you some outlook and summary. So, of course, before the 2D materials, there were very successful demonstration of the spin transport. And in bulk materials, for instance, in the metals like aluminum, copper, silver, there were like a very nice demonstration of the spin transport. And in particular, the group of the Bart van Wees, Otani, and also Mark Johnson, they demonstrated that the spin transport in most of these materials, it exists up to room temperature. And this metal spintronic, it has some advantages like room temperature operation. But generally, as you can see here, the spin relaxation lengths are quite small. And also the spin signal that we measure, it's in the order of 1 microvolt. It's quite small. So for application, this could be like a bit like a big challenge to solve. But of course, over the time, there have been like so many advancements in the metallic spintronics as well. One of them, it came from the Otani's group from Raken. And indeed, they were working with the silver-based spin valves. And they had also a bit different device geometry. First, they had like a ferromagnet, chrono, and then a tunnel barrier. And then finally, finally at the top, there were this spin conducting channel material, which was silver. So they did the annealing. And with the annealing, they could improve the tunnel resistance considerably. And then as a result, from 1 microvolts of the spin signal, they could increase it almost 100 times. And you can also see that now they start to realize in metallic spin valves spin relaxation length over a micron. And similarly, spin transport with semiconductors were also realized, and it was very exciting indeed. And once you work at the low temperatures, these materials like gallium arsenide, silicon, and germanium, they show the best spin transport properties. For instance, in gallium arsenide, I guess the spin lifetimes in the order of tens of nanoseconds at the base temperature, but you can see that the spin signal just die about 80 Kelvin. So majority of the spin transport studies were limited at the low temperature, but at low temperature, the spin relaxation lengths were very long. And basically, you can also control the spin transport by changing the doping in this material, the conductivity of sample, and also the spin transport properties. So one of the advancement in this field, it came also from a Japanese group. So what they did is, again, so as you can see, like most of these advancements are just coming from the improving the interface quality. Like in this case, what they were doing is like just before the growing the magnesium oxide and the ferromagnetic electrode, so they were just like doing the HF treatment to the silicon to remove this natural oxide, and they could see the spin transport up to room temperature. And previously, the highest spin transport they could measure was up to 150 Kelvin. So this was, I think, a very important advancement, and the spin relaxation lengths were in the order of spin relaxation times were still like in the order of nanoseconds at room temperature in this device. And here I also want to make a comment that all the spin Waals devices that I will be talking today, they are based on this non-local four-terminal geometry. So here you are completely separating charge and spin, and then you are just measuring the pure spin voltage. And there were already like some very good demonstration of the room temperature spin transport by Saroj and also other groups at room temperature by using the three-terminal Hanle. But since I want to be consistent in my presentation, I'm just showing the four-terminal devices. Okay, so here I listed the metals and also the semiconductors, and you can see that they are both advantages. And in the case of the graphene, that was the idea that it was almost inheriting the advantages of the both metals and semiconductors. And because of like very high mobility, electronic charge mobilities in graphene, and carbon is very light atom, and the spin-orbital coupling is very small and almost no hyperfine interaction. So all of these were translating into expectation of very long spin relaxation lengths. And the first results came from the Bart van West group in 2007, and they demonstrated room temperature spin transport and with the spin relaxation lengths in the order of 1.5 micrometer. So the results were quite nice. It worked at room temperature. It's over micron length, but indeed theoretical expectations were in the order of hundreds of micrometer, and spin lifetimes in the order of microseconds. So it's a bit off from the theoretical calculation, but the results, the first results, were very exciting. And there were like lots of efforts to improve the spin relaxation spin parameters in graphene. So one of the approach was improving the graphene's electronic mobility so that you increase the spin diffusivity, and therefore basically the spin relaxation length increases. So here, for instance, it was demonstrated that encapsulated bilayer graphene, it can have like spin relaxation length in the order of 24 micron at room temperature. And the second approach was rather than just the spin diffusion, it was to improve the spin relaxation times. And in this case, the paper that I just showed with the silver spin Waals, the inverse spin Waals, so very similar devices were made with graphene as well by Ahmet group. And in these inverted spin Waals, they could see like spin lifetimes of 13 nanosecond and spin relaxation lengths of 30 micron. So these are the longest spin relaxation lengths measured in any material system at room temperature up to now. So it's quite remarkable. And so the question is like, if we have really like very good spin transport properties, can we start to think about applications based on this material? And this was indeed the first project in my PhD, and we were thinking we borrow some large-scale CVD grown by the SKKU, and then we started to do the spin transport, very simple ones on the regular conventional silicon oxide substrate, and we could see that the spin transfer properties was as good as isolated. So we start to think that, okay, this could be a good way to go for the applications as well. And then a theory paper came indeed from Stephen Roche group in 2019. Basically, they show that the spin relaxation is not disturbed by this polycrystalline or grain boundaries. And then Venkata, his group, they showed that the spin relaxation lengths of 13 micron with the spin relaxation of times of the 3.5 nanoseconds have been obtained in the polycrystalline large-scale graphene, which is amazing. Like, so with this, you can start to consider about making like a very exciting, complex spin device architectures. And one of the first very nice demonstration came from the Saradash group from Sweden, and they realized like this kind of complex device circuits, and then they demonstrated, they showed the communication between the different arms, and I think it's a very important demonstration towards the application of the graphene spintronics. And besides that, there are more for the graphene spintronics. So indeed, there is spin orbitronics, as I mentioned. Iris gave a nice talk, Saraj gave a nice talk about this. So in 2014, we were first considering about studying the spin proximity effect in graphene by combining with the TMDCs, and we could see like spin Hall effect, inverse spin Hall effect in graphene at once the Fermi level was in the electron site. And later on, people have like more deeply investigated, and now I can say that the field is like very much established, and it's one of the hottest topic in the graphene spintronics. And in terms of the spin injection, so optospintronics capability in graphene was not realized before, and it's mainly because, as you know, graphene has very low spin coupling. And also, it's a semi-metal, its optical absorption is extremely low. So you cannot really do like any optical injection into the pure graphene. So what we thought is like, okay, there is like transition metal dichalcogenide monolayers, which have like a very strong optical absorption property. And these materials are also quite interesting that due to like broken spin degeneracy and also time reversal symmetry, these materials have like a very interesting spin Waals physics. So spin and Waals, they are coupled in a way. If you send a circular polarized light, you can excite one of the Waals, which has like a well-defined spin orientation. So basically, you can generate the pure spin current. And then the idea was like we generate through the TMDC, they diffuse into the graphene, and then we non-locally with the electrical contacts, we just measure it. And then we got some nice results, and at the same time, in fact, a bit before than us, Roland Kawakami's group, they also used the same, they had the same device geometry, and in fact, they measured at room temperature that this optical spin injection is working very well. And I must also give the credit that Yaroslav Fabian's group were the first one who proposed this. And I was happy that it was working quite nicely. And there are two more experiments which excite me, and I would like to briefly mention. One of them is like a non-local spin transfer torque effect by using the graphene. So the idea is like you generate the pure spin current, and then by using this pure spin current, you change the polarity of the detector magnet's polarization direction. And this was previously realized in the copper-based spin Waals by the Otanich group. And here in the case of the graphene, it didn't work as planned, I guess, because you need to still like assist with the magnetic field to see the effect. But I guess with the device optimization, this could be realized without any external magnetic field. And this is very important for these all spin logic devices that I show at the introduction of my talk. And yeah, once we're talking now about the logic operations, there was already like some demonstration of some logic operations in graphene. One of them was this exclusive OR demonstration by the Kawakami's group. So here they just changed the polarity of the magnets with the magnetic field, but the idea is like they could change the spin accumulation under this electrode, and then they could see these exclusive operations, which is again I believe quite important for the applications aspect. And we tried to build some heterostructures by using the HBN, etc., and dual gated devices to study some interesting spin transport properties in graphene. And here, as you can see, like we had like some boron nitride, we etch it and then later on transfer on top of the bilayer graphene, which was deposited on the boron nitride. Okay, and then by using these openings with the injector and detector electrodes and these HBN regions by using some top gate electrodes, we realize the spin valve devices, dual gated spin valve devices. And in this device, we could already see that the improvement in the spin lifetimes as mobility was increasing or as it was getting more encapsulated. And in these devices, we could study the spin relaxation mechanism. And so let me show you a bit like the background of that. So in graphene, as I mentioned at the beginning, there were like two spin scattering mechanisms was considered. One of them was Elliott-Yafet, the other one is the diagonal pair. If you just like you really just think about the usual transport parameters which were observed in the experimental values, into this equation, you would expect like spin lifetimes of the microseconds. But these are like at least 2 orders of magnitude better than what we see experimentally. So there were some consideration if the relaxation mechanism in graphene is a bit different. So one suggestion came from the Stephen Roche. He said that because of the spin entanglement at the ballistic region, this could be the reason for the spin dephasing. And another relaxation mechanism which took my attention was this resonance scatterers. So basically, they don't contribute to the charge momentum relaxation much, but it's mostly the spin relaxation. So what's happening is like you have like a resonance scatterers with a magnetic impurity on top, okay, and then your spin comes and spends some time around it, and depending on how long it stayed there. And there is an exchange between spin and the impurity, and then at the end, after this resonance scattering, we see that the spin is 50% is flipping. And by using this simple idea, Denis Kochan and the Yaroslav Fabian's group, they could already obtain the spin lifetime values that we observe experimentally. And in this study also, there was like an interesting suggestion for the experimentalists. So the idea is the following. So they were saying that you can confirm if this is the spin scattering mechanism by looking how the spin lifetimes are changing with the energy of the carrier concentration. So the basic idea was like this spin relaxation time or relaxation rate is split because of the single and triplet splitting, and this splitting amount is different for single layer and bilayer graphene. But in these materials, there is also a broadening coming from the thermal energy, thermal station, and also the electron hole puddles. And they say that since the density of states for bilayer graphene and single layer graphene are slightly different, so this would have like a different impact on how the broadening is impact on this lifetime versus energy. In the case of the monolayer graphene, single layer graphene, so they predict that the single layer graphene, the spin relaxation time should increase as you increase the carrier concentration. In bilayer graphene, they predict that first spin relaxation time should decrease, and then a density around 3-4 times 10 to the power 12, it should start to increase. So with this in mind, so we start to do like a gate-dependent spin transport measurement. In the single layer graphene, we could see that as you increase the carrier concentration, spin relaxation time was increasing. In the bilayer graphene at the low doping regime, we could see that the spin relaxation time has an opposite tendency than the single layer graphene. And by using this dual gated bilayer graphene, you can dope a bit higher. And we could see that around 4 times 10 to the power 12, spin lifetime start to increase a bit. So I'm not claiming this confirmation of the this resonance scattering via these magnetic impurities, but I think our experiment was kind of suggesting, supporting that idea. And in this heterostructure device, you could do something more. We did like some PN junctions, etc. But another thing we could do is like the controlling the spin signal with the gate voltage. So in monolayer graphene, what's happening is it's a semi-metal. It's a metal basically, and the change, even though it's like monolayer, the change you can have in the resistivity of the material is very small with the gate voltage. So it's also the same for the non-local signal. With the gate voltage, you can really change the spin signal very small. At least you cannot make it on and off, which you would expect in a semiconducting material. And in bilayer graphene is a special material. So if you apply like a large displacement field, you can induce a band gap at low temperatures. So this is something that we were trying to look. So this is like we had like very bad band gap opening, so it was like quite disordered. But we could see already that the risk at the direct point was changing 5 times. And we start to do like spin transport along this direction once the carrier concentration was fixed, but we increased the displacement field. Therefore, we increased the band gap of the system. So what was happening is that near the almost no electric field, we see like regular spin transport and Hanne. And as you start to go more, increase the displacement field, we could see that we can like completely shut down the switch of the spin current. And it could work like as a kind of like spin switch effect in bilayer graphene. But this only works at low temperature, and it's partially because this material has extremely low band gap. Okay, and if you want to really revise this kind of device concepts, there are already like some 2 nice demonstrations that graphene TMDC heterostructures spin transport was shown to be like gate dependent, and you can switch on and off, or you can just use a semiconducting material without any of these tricks. So that's how we like indeed like start with the black phosphorus spintronics. And black phosphorus is a special material. If you look at the periodic table, it has like you can already see that the spin coupling strength shouldn't be that high. It's like neighbor to the silicon, which is another star material for spintronics. And this black phosphorus, it has it's a semiconductor basically. Once this material is in the bulk, it has a band gap of 0.3 eV. But once you go to the monolayer, it starts to become gaps start to increase above 1 eV. And because of that, we could also see that the on-off ratio was changing with the thickness. But this material at room temperature is a semiconductor, and you can have like a decent on and off. And what's cool about this material is the mobilities that we had with this material was extremely high. So for instance, like at room temperature, it was reported the mobilities are around 5,000. At the low temperature, it was around 45,000. And besides, it has also like some pocket structure, charge or spin diffusion as well, could be like depending on the crystal orientation. So this material has like lots of interest for spintronics. And but of course it has some problems, otherwise it will be so trivial. So what happens is like in this device, if you expose it to air, you can see within 1 hour just the material is degrading. And we try to work on it, how to fix this, and then we build a Drawbacks with a transfer stage inside. And here my colleagues already show, you can see these dash areas, they transfer some monolayer graphene. And they demonstrated that if they keep this material in air after the encapsulation, these encapsulated regions are staying almost pristine while the device is degrading. So we knew that this encapsulation could be a good strategy to make the material air stable. So, and I wanted to always think about how to make a devices based on that, because if you cannot use, there is no point in making it air stable. So here I came up with the idea of using a graphene as an electrode and encapsulating with the HBN. Everything was done in the glove box, and then after we take it out, since it's so fully shielded, and then we just do the lithography to complete the devices. And in this device, we could see already, like if you measure in vacuum or in air, they show the same transport characteristic. And this is like very good compared to the non-encapsulated devices, where the device transport becomes very unreliable. And we could also see that the sample, even after 2 months, nothing was happening, and it shows still like a hysteresis-free transport characteristic. And after making the stable, so we start to think about making the spin walls based on the black phosphorus. And the idea was like, we need to fully encapsulate with the HBN, between HBN, so that it's air stable. And also this top HBN will work as a tunnel barrier for efficient spin injection and detection. And this bottom boron nitride will be working as a high quality, like a dielectric substrate to enhance the mobility of black phosphorus. And these are the optical pictures of the devices, one of the devices before and after the metallization process. And everything was done in the glove box in terms of this encapsulation. And there was no polymer involving in the transfer. So interface between this HBN, BP, and the HBN is pristine. So it's very high quality. And before we start to see the spin transport, we already see that the devices are working differently than what we were expecting. So in some devices, we had like some encapsulated regions, some regions without any encapsulation. And if you look at the non-encapsulated region with the direct cobalt contact to the black phosphorus, we see like regular p-type transitor behavior that you would expect from black phosphorus with the hysteresis, and it's normal because it's not encapsulated. But once we start to look at the encapsulated region, the material was completely n-type, and of course it was hysteresis free, it was high quality, but we were very surprised that the material shows like P or N-type, depending on having a HBN in between the cobalt. And we wanted to explain this. We collaborate with the Su Ying's group from NUS. But I must also give the credit that there was a PRB paper before, which was predicting theoretically what I'm going to show now, that because of the dipoles at the surfaces. So basically, this theory were saying that the effective work function of the cobalt is decreasing if you insert the HBN. So the based on our calculation was showing that it goes from 4.9 eV to the 3.6 eV by just inserting a monolayer HBN, and by putting more HBN, this work function was not changing much. And that's why, indeed, in the case of the here without HBN, we are much closer to the valence band, and in the case of here, we are much closer to, of course, the conduction band. That's why we see like P or N-type behavior. And at the same time, the group of Jameson from Colombia, they also realized this kind of electrodes, cobalt boron nitride for MOS2, and then they also did some XPS studies on the structure, and they could see that the work function of cobalt HBN become 3.3 eV. So by just inserting a HBN, you can completely change the work function. And in these devices, we could already see like extremely high mobilities. So we could see like mobilities of easily like 4K at low temperature, and even like two terminal, we could see like this nice transport characteristic. And then we start to do the spin transport measurements. First, like this is indeed the first sweep I did. So I'm putting this purposely. So the separation between the injector and the detector electrode was around 2.7 micron. And we could already see like a very nice spin Waals switch. And by doing the spin 100 precession measurements, and we could excite the spin transport. We could excite the spin transport properties, parameters. Like for instance, at 100 Kelvin, we could observe like in this device lifetime of 3.2 nanoseconds with spin relaxation length exceeding 6 micron. And we could see that the spin transport also like at room temperature. And we have some unpublished results in the spin transport it could be like up to 4.4 nanosecond. And we could see like much higher non-local signals at room temperature. So these results will be published. And so the spin transport in black phosphor works. It's a semiconductor, and we have now a semiconductor which works at room temperature. And we wanted to also study the spin relaxation mechanism in these materials. So what we did is we studied the spin lifetimes and momentum relaxation times with respect to temperature. And what we could see is like in the devices we studied, both of them were scaling had like same function, same dependency on the temperature. And so this is like directly indication of the Elliott effect mechanism. So basically spin relaxation is spin flipping is happening during the momentum scattering events. And we collaborate with the Yaroslav Fabian's group. They calculate the spin mixing probability for just like considering the spin orbit of the spin orbit coupling of the host material like black phosphorus here. So this spin mixing probability they found is almost the same with what we see experimented. So I think this is one of the nicest demonstration of the Elliott effect mechanism in a material system. And I have to also say that the spin signals that we see in black phosphorus is extremely large. So you could see like easily like 300 ohms of the spin non-local signals, and it's not coming from the Joule heating. So, and the average was in the order of like 50 ohm of the non-local signal in this material. And I have to also say that the reason we see again these very nice spin transport properties in this material is the tunnel barrier. So once I was showing the advancement about in the metals and semiconductors, like in silicon and also the silver case, I show purposely because like most of the time these materials they show like very nice spin transport properties. It's also the same for graphene, but generally like the spin relaxation could be like limited in the contacts or like the quality of the tunnel resistance. So before indeed starting with the boron nitride in the Drawbacks, I made like characters more than 10 samples with this conventional MgO barrier. And we never saw any indication of the spin signal, which could be also related, of course, with the surface of black phosphorus, which is getting degrading. And in the case of the boron nitride, we characterized this tunneling property of the boron nitride, 3 layers boron nitride that we use. And so like for a good tunnel barrier, there are some criteria. One of them is like of course, IV should be nonlinear, and this IV should also have like a weak temperature dependency. And this was discovered also in graphene in high quality tunneling devices by Roland Kawakami's group. And first it was Makawa's idea that this non-local signal should be reverse the proportion of the conductivity. So our devices our tunnel barrier were showing all properties that you would expect from a high quality tunnel barrier. And again, by using just this like 1.2 nanometer thick of HBN, we were not just using it as a tunnel barrier, but we were also encapsulating it so that we were seeing like very high quality hysteresis-free transport characteristic in this device. And of course, again, we come to the original motivation. This material is a semiconductor. Once it's at on, we show that indeed you can change the spin transport properties by changing the gate voltage. And what happens is like first in almost all devices we measure consistently, we had like more results which are not published. as you increase the gate voltage at the first, it's increasing, and then later on it starts to decrease at high gate voltages. But you could see, like, independent of the gate voltage, we are almost every time like above the nanosecond spin lifetimes range. And yeah, you can also use the spin and the momentum relaxation as a function carrier, and it was also showing that the direct relation, which was another indication of the idiotic effect in this material. And since this is a semiconductor, once you go to the below the threshold voltage for the semiconductor to be off, then this, of course, spin current was also becoming like completely turn off, like I was showing in bilayer graphene case, that you can make also the spin transport, of course, on and off by just changing the gate voltage. But this mostly related to the charge property rather than the spin. Okay, so I think I'm good with the timing. So I will not keep it longer, but in summary, I hope you were convinced that the graphene is the one of the best material for the long distance spin communication, and there have been already very good demonstration, very recent demonstrations about the ideas of using the graphene in the complex device architectures. And there is also now like optospintronic functionality, and the spin orbitronic aspect is also quite interesting. In the case of the black phosphorus, this is very good for the semiconductor spintronics. So you can control the spin transport properly by with the gate voltage. We see a very large spin signal. So this could mean also that these non-local spin transfer torque studies, black phosphorus could be considered, and lifetimes are quite nice. So here I am trying to compare the spin lifetimes measured in many interesting materials. Again, these are just measured under the 4-terminal configuration. So this is like all published, like some of our unpublished, and you can see that the black phosphorus, graphene, and silicon, they are most ideal material system for room temperature spin transport. And here I also compare, and I guess one of the coolest thing about black phosphorus is also observation of extremely large spin signals. So as an outlook, there are a lot of things to do with the black phosphorus. One of them is definitely the anisotropy. So there is already like some demonstration of the charge anisotropy in the black phosphorus. It's like a factor of almost 10 demonstrated between the armchair and also zigzag edge. And independent of the discharge mobility being different, but there is also a fact that the spin of covering strength will be also different. So at the end, there is a possibility of direction control of the spin transport. And with the electric field, you can do many things. You can change the carrier concentration and also carrier types. And with the thickness, you can manipulate the mobility, and also you can also manipulate the spin properties. And one of the things that is half nuclear spin of the phosphorus atoms that could be used to study these nuclear hyperfine interactions. And so, like the first point I came was like, yeah, now we start to have like very interesting material systems, like 2D magnets and 2D good spin conducting channel materials, etc. And I think the research of the 2D van der Waals based spintronic devices getting more interesting, and now there are possibility of like constructing this van der Waals device to realize some innovative memory concepts, etc. So you can already see this nice review article which is focusing on that. So with this, I would like to also acknowledge my collaborators, Barbaros Antonio in Singapore, and Junior, my kind of co-supervising student, and the optical injection I did with Andras and Dimitri at EPFL, and we got the crystals from the Taniguchi and Watanabe from NIMS, and theory was done with Yaroslav, Fabian, Marcin, and Martin, and Ivan from Manchester was also quite helpful while he was in Singapore for a short time. So he was also working with me on bilayer graphene spin Waals. So with this, I would like to thank you, all of you. And if you have like any students, master students or undergrad students who are interested in doing the PhD, yeah, let me know. We have like some openings soon. So thank you.
Thank you very much for the lecture, for the very interesting talk. So this talk is open for questions. You know the drill. If you're on Zoom, please use the raise hand function. If you cannot find it, you can always send me a private message. And if you're joining us on Twitch, and if you have any questions, you can type it in the chat box, and I will read it for you. Okay, let's see. Okay, let me ask the first question. For the black phosphorus, are you able to do optical spin injection?
That's one of the ideas that I want to do, but so far we haven't done it. But I think for optospintronics, it's more suitable than the graphene itself.
I see. Thank you.
Yeah, but so far nobody has done anything.
I see. All right. Any questions? I want to ask another actually question for the in the Outlook. You mentioned that there are some devices proposed using the combination of 2D ferromagnets and the graphene or black phosphorus. If you just do the non-local spin injection experiment, has anyone already done that using a 2D ferromagnet on top of graphene?
Yeah, this is something. Yeah. While I was at EPFL, I was not directly working on the spin Waals, so I was more doing other things. And I was very curious why nobody has demonstrated that. So I think it's a very good idea.
But
yeah,
can you comment on if there's like you can imagine any potential challenges?
Yeah, no. To be honest, I would expect it to be much easier than the conventional magnets.
I see.
So the idea is like. With the ferromagnet, for instance, like in graphene, once you evaporate the cobalt or magnesium oxide, so you can first of all create some defects, etc. So, so the interface is not pristine, right? And in the case of these 2D magnets, frankly speaking, the interface is just like van der Waals and pristine. It could be much better. The second thing is like with these materials and with these conventional magnets, the conductivities are still too different, and you have like this conductivity mismatch problem. But by using like these 2D magnets, some of them, they could have like comparable conductivities with your non-magnetic channel. So there is even like some possibility that you might not need even a tunnel barrier for spin injection. So I think that there are so many nice opportunities, and I'm sure many people are working on it.
I see. All right, any other question from the audience? Boris, please go ahead with your question. Please unmute and you can ask your question yourself.
Yes, it's a very nice talk, and congratulations on the new position.
Thank you.
My question is, for black phosphorus, has anybody done, or you or anybody done freestanding films? It must have been. And do you expect any significant advantages or differences if you do that?
No, the problem is like you really need to seal the black phosphorus. So if you suspend it,
right,
then the bottom part is still like get some airs penetrating, right? So bottom part will be still like kind of degrading. So the idea is like you fully encapsulate it so that there is no air going into your black phosphorus.
Mm-hmm. Okay, and another question is, are there any problems with the Schottky barriers you talk about phosphorus compared to?
So by using the boron nitride, indeed here I'm not showing unfortunately, but by using the boron nitride we also of course studied this Arrhenius plot, and we see almost like no Schottky barrier in our devices. The height of the barrier is almost zero. So it's like the charge injection is purely like tunneling based.
Okay, thank you.
But if you have like direct cobalt contacts, there are also nice work by Saroj Dash group in, I guess, in advanced material. you can see that for the direct cobalt contact to the black phosphorus, there's a Schottky barrier in the order of 50 to 100 MeV.
Thank you.
Thank you.
Thank you. And Kirill, please go ahead with your question.
Yes, so you mentioned the anisotropy of black phosphorus. Can you say a couple of words about the band structure? Anything noteworthy there, like valleys or,
Yeah,
what
so
is it like?
in the case of I guess the black phosphorus, not the valleys, but there are some calculations, I guess, like if you have like thin doped black phosphorus, you might have the valleys, but pure black phosphorus, I guess, is not that interesting in terms of the electronics, as far as I know. And in terms of the anisotropy, yeah, people have shown that the anisotropy along the armchair is almost like 10 times the more conductive than the along the zigzag edge.
So
And there are also some spin lifetimes predictions based on the crystal direction, which shows that there is almost an order of magnitude difference in the spin lifetimes, and this could even like enhance if you apply some electric field.
is this because of the effective mass anisotropy?
Yes, yes. Effective mass is different. That's I guess the biggest contribution.
And is that similar for electrons and holes?
No, it's that's another very good point. This anisotropy is different for at the valence band and also at the conduction band. So yeah, how to say, so like if you do these anisotropy measurements, anisotropic spin transport measurements as a function of the carrier concentration, if you combine these two, you will see like a maybe 20-fold difference in terms of the spin lifetimes, etc.
Okay, thank you.
Thank you.
Okay, do you have any other question? If there's no other question, I would like to thank the speaker again. We'll have another off-the-record discussion with Professor Avsar soon. But let me take this opportunity to thank all of you for your kind support to the online Spintronics seminar. It's been an honor and a very fulfilling experience for Kirill and me to be hosting these seminars. We'll continue on next year, bringing you exciting talks. Before then, Merry Christmas and Happy New Year to you all.